Hi everyone, my name is Chico. I am from the University of California, Irvine. Here is the topic of my presentation. This is a collaborative research work between 3 university labs at UC Irvine. We are developing a pedestrian navigation system that tracks people in a self-contained approach. Developing an accurate and reliable pedestrian navigation system can enable location-based services in many applications, such as healthcare, entertainment, retail store, and public safety. In this research, we focus on public safety domain, and we are developing a pedestrian navigation system for firefighters and first responders. Developing such a navigation system is not trivial because firefighters and first responders are often required to navigate in both indoor and outdoor environments. In outdoor environments, GPS provides reliable and accurate navigation solutions. However, in indoor scenario, its signals are too weak for acquisition and tracking. Therefore, alternative localization technologies are needed. There are many potential technology candidates that has been developed for this process. This technology includes camera, LiDAR, Bluetooth and Wi-Fi, ultra-wideband, cellular signals, pedometers, and inertia navigation system. However, a system dedicated to firefighters and first responders needs to satisfy very strict requirements. These requirements include environmental independent, infrastructure-free, consistent availability, and long-term stability. While using this technology independently might be challenging to cover all the situations in firefighting scenarios, some of these systems have complementary properties that can be integrated together to achieve reliable firefighter localization solutions. In this research, we are using inertia navigation system as the core technology with enhancement from ultra-widebands and cellular signals. Inertia navigation uses IMU and perform the strap-down inertia navigation algorithm to estimate orientation, velocity, and position. It is well understood that these navigation solutions has errors accumulated very quickly, and this error is proportional to the cubic of elapsed time. A popular and very effective approach to limit the error growth in a standalone inertia navigation system is an algorithm called the zero velocity update, or ZUPT. The ZUPT algorithm uses foot-mounted IMU and assumes that in the human gait cycle, during the stance phase, the velocity of the foot is very close to zero when it's touching the ground. This information can be used to periodically reset the velocity errors. In the conventional implementation of the ZUPT-Aided inertia navigation system, we're using a common filter. The prediction step of the common filter is a strap-down inertia navigation system. In the update step, when a stance phase is detected, a pseudo measurement of zero velocity is feedback to the common filter to update the velocity state. This navigation solution has been analytically predicted and experimentally demonstrated to have a position error of less than 1% of the traveling distance. This is a significant improvement in navigation accuracy as compared to a standalone inertia navigation system. However, the ZUPT algorithms has been identified with long-term drift issues. The long-term drift issues mainly come from the fact that yaw angle and position state in the common filters are not, the errors are not bounded. In a typical firefighting scenarios, the accuracy requirement is to have an error less than 1% for a duration of approximately 30 minutes. If we're using a low-cost IMU, the ZUPT algorithm is not sufficient to address the firefighter localization problem. Therefore, additional enhancement techniques is needed. In this research, we enhanced the foot-mounted IMU via sensor fusion solutions with multiple different sensing modalities, including barometers, foot-to-foot ranges, LT receivers, and ultra-wideband. The barometers and foot-to-foot range measurements are considered as self-contained aiding techniques, and their measurements are always available. Therefore, these techniques are considered as the deterministic approaches. LTE receivers provide quality position enhancement opportunistically depending on the locations of a building. Therefore, we call this approach opportunistic navigation. For ultra-wideband modules, we deploy the sensors on a group of firefighters, and the range measurement between each of the ultra-widebands are used to update the relative positions between each firefighters. Therefore, we refer to this algorithm as the cooperative localization approach. In the following slide, I will discuss detailed implementation of these three different functionalities. Let's start with the deterministic approach. Stance phase detection in the zero velocity update algorithms is very important because its detection performance directly affects the navigation accuracy. We perform the automatic stance phase detection based on likelihood ratio test. In this framework, a likelihood statistic is computed based on accelerometer and gyroscope measurement. This statistic is compared with a predefined threshold. Here is a profile of the likelihood statistic collected during a pedestrian walking experiment. We can use a threshold to differentiate between stance phase and swing phase. In the deterministic approach, we use barometers to enhance the vertical displacement errors. The barometers measures absolute air pressure, and these measurements can be converted to estimated height based on Earth's atmosphere model. Here is an example of the barometers operating in a controlled indoor environments between different floors. In the deterministic approach, we also use foot-to-foot range augmentation to increase the yaw angle observability. This implementation is using a dual foot-mounted IMU mechanisms, and on the foot we also have a set of range sensors. The measurements between the range sensors are called the foot-to-foot ranges. These measurements is used to update the predicted foot-to-foot ranges in the common filters, and the mismatch between the prediction and the measurements are the estimated errors. These estimated errors is used in the common filter to update the navigation state. In opportunistic approach, we leverage the LTE signals to provide global position compensation using LTE pseudo-range measurements. Two techniques are applied on the opportunistic approach. First, we use a base rover framework. The base rover framework is used to mitigate the problem of clock bias drift. Assuming we have a fire truck parked outdoor, on the fire truck we install GNSS receiver and a base LTE receiver. The GNSS receiver is assumed to have access to clear sky. And we have a rover LTE receiver installed on firefighters who will be navigating in indoor environments. The rover LTE receivers and the base LTE receivers will be connected to the same LTE towers, and the base LTE receivers will be used to estimate the clock bias drift of the LTE towers. This information will be transmitted to the rover LTE receivers to mitigate the pseudo-range errors. Another approach we're using in opportunistic navigation is synthetic aperture navigation. This approach is to mitigate the effect of multipass based on beamforming technology. We're using synthetic aperture array instead of a physical antenna array to realize the beamforming process because cellular signals carrier frequency is around 731.5 MHz, which corresponds to a wavelength of 41 centimeters. This is for the case of T-Mobile. If we use a physical antenna array of 10 components with spacing of half of the wavelength, then we would need a hardware size of larger than 2 meters, which is not very practical in real-world application. The synthetic aperture array we're using uses a single antenna. We explore pedestrian motions to collect signals at different locations to form a synthetic antenna array. All the signals collected within a specific time windows are used in the beamforming process, and with the beamforming process, we mitigate the effect of multipass. Here I'm showing you a high-level overview of the LT synthetic aperture navigation framework that we just talked about. In this framework, we have a LT receiver, a beamformer, and a common filter. What I'd like to highlight here is that in the conventional LT beamforming process, we are using spatial smoothing and estimation of signal parameters via rotational invariant techniques. In the most updated approach, we're enhancing these two functionalities with deep learning. If you're interested in the details of all these block diagrams, you can find this information in our paper. In cooperative localization approach, we use ultra-wideband sensors to provide relative position enhancement between multiple firefighters. In this approach, we assume a group of firefighters equipped with localization module and ultra-wideband module. The localization module produces estimated position as well as position uncertainties. Each ultra-wideband modules are connected with each other, and information including inter-agent ranges, position estimates, and position covariances are being exchanged between each agent. The essence of the cooperative localization approach is that the agent with smaller position uncertainty will increase the position accuracy of agent that has large position uncertainties. To maintain the quality of the ultra-wideband signals, we use two techniques. First is a non-line of sight detection. We use probabilistic power matrix models to perform the detection. Here I'm showing you a power matrix profile collected during the line of sight scenario and non-line of sight scenario. Then we can compute the probabilistic matrix based on the power matrix measurements and assign a threshold to identify line of sight situation and non-line of sight situation. Another technique we're applying to the ultra-wideband signals is range bias compensation. We perform this compensation by utilizing a neural network approach. This is the configuration of our neural network. It has an input vector of 4 different physical quantities, and the output of the neural network is calibrated ranges. Now I'm presenting to you an overview framework of the pedestrian navigation system integrating deterministic, opportunistic, and cooperative functionalities. In the deterministic approach, we're using dual foot-mounted IMU plus zero-velocity update algorithms, parameters, and foot-to-foot ranges. In the opportunistic approach, we're using LT signals and implements synthetic aperture navigation and base robot framework. In the cooperative functionalities, we're using ultra-widebands to collect inter-agent range measurements. All these informations are fused inside the common filters, and these common filters is implemented on multiple different agents to achieve multi-agent pedestrian navigation system. In this research, we developed a pedestrian navigation testbed that includes the 3 different functionalities. In the deterministic approach, we're using the Lab-on-Shoe platform. The Lab-on-Shoe platform is developed in UC Irvine Microsystems Lab as a very flexible platform so that we can quickly and effectively investigate different algorithms and sensors. The Lab-on-Shoe platform is upgraded with cooperative ultra-wideband modules. The LT receivers used in the opportunistic navigation is installed on the backpack. The laptop held by the person that you're seeing here is used to collect all the sensor measurements from the system. Inside the backpack, we have a digital signal processing unit, laptop, a storage unit, and a battery. On the Lab-on-Shoe platform, we have 2 shoes, and on each shoe we have an IMU, ultrasonic sensor, barometers, ultra-widebands, microcontrollers, Bluetooth modules, and battery. We use this navigation testbed to evaluate our developed integrated system that combines deterministic, opportunistic, and cooperative functionalities. We conducted experiments in indoor environments at University of California, Irvine. In the main screen, you're seeing a red trajectory and a virtual environment. The trajectory was produced by our navigation solution. The virtual environment is a point cloud dataset constructed by a smartphone LiDAR and camera module to illustrate the environment of our experimental scenarios. The bottom right video shows the experimental process, and the bottom left video shows an animation of the received LTE signal carrier to noise ratio. In the experiment, there were 3 agents. One of them is what you see in the video, and the other 2 are assumed stationary at the other parts of the building that you'll see later in the video. Each of the 3 agents has a local position error propagation, and they were connected with ultra-wideband modules. We performed cooperative localization to compensate their relative position. The moving agent you're seeing here in the video traveled through multiple different indoor terrains, including stationary period, straight line segment, going up and down stairs, and riding in elevators. And this experiment was conducted in deep indoor environments, including corridors, office space, staircase, and etc. During the experiment, we surveyed multiple checkpoints in the environment to evaluate the navigation accuracy of our navigation solution. At the end of this experiment, the agent returned to the original position. So this is a closed-loop experiment. This is the experimental scenario you just saw. The navigation duration was around 14 minutes, and the length was around 600 meters. This is the experimental result estimated by our navigation solutions. The blue and the red trajectory correspond to the left and right foot of the moving agent. Survey points are marked with green triangles. In this research, we compare with an extensive combination of navigation approaches, and we perform the evaluation of the navigation accuracy based on different metrics. I'm not going through all the approaches. If you're interested, the information together with explanations and discussions can be found in our paper. The main takeaway here is that if we use standalone deterministic approach, we have a position root mean square error of 0.97 meters and a final error of 1.76 meters. If we use either cooperative localization or opportunistic navigation to enhance the deterministic approach, the navigation errors can be reduced. Lastly, the solution integrating deterministic, cooperative, and opportunistic functionalities has the best navigation results in this experiment. In conclusion, we are developing a pedestrian navigation system for firefighters and first responders in this research. Our solution is to use foot-mounted IMU augmented with barometers, foot-to-foot range measurements, ultra-widebands, and LTE signals. We developed algorithms and hardware framework to realize the navigation solutions. And we conduct experiments in indoor environments with a trajectory length of 600 meters in 14 minutes, and the navigation solutions was less than 1 meter. Lastly, I would like to thank our funding agency NIST for support our research. Thank you for attending our presentation. I'll be happy to take any questions.